this last section in chapter 3 is titled Modeling Using Variation. Variation is a way for variables to either uh, kind of depend on each other in a direct way or an indirect way. Basically, coming up with two types of equations, either linear or rational. And we're going to see those both. Um, I feel like it's pretty straightforward. Granted, it is word problems, but they all kind of work out to be the same. So before we jump into the first application here, the language is really important with these variation problems. So if a situation described by an equation in the form, this is going to be direct variation. If we know that we have direct variation, your equation is going to be y equals k times x. K is a non-zero constant, and so really what we're seeing here, this is simply just a linear equation. Okay, linear equation with a y-intercept at 0. That's all that it is. All right, now the language part of this is definitely one thing we're going to add into our notes, and so you're going to see in these given problems that'll say y varies directly as x, or y is directly proportional to x. And so basically what that is describing is as x gets bigger, y is also going to get bigger, okay, and vice versa. Okay, direct variation, both variables are going to increase and or decrease at the same rate, which aligns with what we know about linear equations, right? It's a constant growth, and both x and y are either increasing and or decreasing if it ends up being negative. So it's just about all these problems. What we're going to end up doing is we're going to want to build the equation. We're going to be given some values of x and y that'll help us find that constant, the value of k there. And then we're going to plug in a value to then kind of solve the actual problem there. I added these cool pictures for all of them. So I'm being a vampire because it's about blood. And it says the volume of blood, B, in a person's body varies directly. That part's really important because that's going to tell us how to set up our equation. Varies directly as body weight W. Now, when you look at how this language is described and what we took note of to start is y is usually going to be the first variable that's described. Okay, so when we say that the volume varies directly as the body's weight, it's going to be the volume of blood, so B equals K times the weight. No, it makes sense, right? Like the bigger you are, the more volume of blood you're gonna have in your body. Yeah, I don't know. I don't know how true this is, to be honest. There's a reason I'm a math teacher. I don't know. My science facts are iffy, iffy. So I don't know. Anyways, a person who weighs 160 pounds has approximately 5 quarts of blood. Okay, so then we're going to use that to estimate the number of quarts of blood in a person who weighs 200 pounds. But before we do that, we need to find this constant, the non-zero constant K. So it says that the volume here is 5 quarts of blood for one person that weighs 160 pounds. And so we can easily solve for the constant by dividing by 160. So K is 5 divided by 160. Let's leave this in fraction form. That's one thing that we tend to do is leave things exact. But we do want to reduce it down, and I can reduce it down. Remember the calculator does this for us. I can go 5 divided by 160, and it's going to give it to me in a decimal. But then if you find the math button, and other calculators usually have this option too, but for the graphing calculators, if I press math, the first option is frac. It's going to take that previous answer and convert it to a fraction for us. So it's 1/32. So we're going to have K equal 1 over 32. And so our equation is the volume of blood, B, is equal to 1/32 times the body weight. And now we can go ahead and use this equation to estimate the number of quarts of blood in a person who weighs 200 pounds. So how much blood? 1/32 times 200. That's really 200 divided by 32, 6.25. So we'd say the volume of blood is about 6.25 quarts. And again, I have no idea how accurate that is. Ask your biology teachers. They'll know, or at least have a better answer than I would. Simple enough, right? All linear equations, not too bad, but it's still word problems. Yeah, Evie? Proportion. I think when it's direct variation, it should. Okay, let's see. Okay, so Evie's asking, would it work just to set up a ratio? So if we took the 160 pounds, and let's say that there's 5 quarts of blood, is that equivalent to someone that's 200 pounds and X? I think it's going to end up working out the same. Okay, only because of the direct variation. So this would be 160X equals 5 times 200. This is a situation where we would cross multiply. So 160X equals, would that be 1,000? And so then 1,000 divided by 160. Oh, look at that, 6.25. So yeah. Usually when we have those ideas, you want to make sure it works for more than one case, but I think with direct variation, we can use ratios if you want to. The way that the Math Excel is set up is it will likely have you come up with this equation, so you're not going to be able to use the proportions, but I'd love for us to see a problem and think about different ways of how we can approach it. So I think that's a really good idea. Okay. We're just going to move forward. We have different types of variation. The problems all end up kind of being very similar, but different applications as we go through this. So we can still have direct variation, but we can add in exponents. Again, the language here matters. So it'll say y varies directly as the nth power of x. And your equation is y equals the constant k and then x to the power of n. Another way that you might see it written is y is directly proportional to the nth power of x. Something more so than just the math itself is us getting used to the language here. And we don't tend to think of language and reading being a part of math, but it is a huge part of math, especially as you start to dive into different applications. All right, I'll give you all a sec to write this down. Okay, let's go through an example with direct variation involving powers. So the distance s that a body falls from rest varies directly as the square of the time t of the fall. If a skydivers fall 64 feet in 2 seconds, how far will they fall in 4.5 seconds? So again, we need to solve for that constant of variation. So in this case, the distance is s equals that constant k, and then the square of the time t, so time squared. And then that we are given that in 64 feet, or they fall 64 feet over the course of 2 seconds. So we have that 64 equals k times 4. When I divide by 4, we get that k is 16. So our equation is the distance s equals 16 times the time squared. So we want to figure out how far somebody has fallen in 4.5 seconds. All we're going to do is plug in 4.5. And I'm going to use a calculator for that one. I'm going to do 16, 4.5 squared. And I get 324 feet. Again, no idea how accurate that is. It would make sense that, don't you kind of hit when you're falling? Don't you hit a speed that is constant at some point? Yeah, right. So that's probably true to a certain point, and then eventually you get to a speed where that is your maximum speed. It's probably not all of that true for most of these. All right, everyone good here? Pretty straightforward. All right. The next type of variation, remember, if I get going too fast, you have those notes on your desks. If you end up not using those, I will take those back, but know that I do have those on there for you. Okay, inverse variation. Similar kind of idea, except this time the language here is going to be a little bit different, and our equation is a little bit different, in that the equation for inverse variation is the constant k divided by x, thus a rational equation. The variable is in the denominator. It is a rational equation. K is still a non-zero constant, and you would see the language as y varies inversely as x, or y is inversely proportional to x. Basically saying as one variable gets bigger, the other is going to get smaller, and vice versa. So if one variable is getting smaller, that means another is getting bigger. So they're inversely proportional. How we're going to set up and solve these problems is the exact same. We're going to be given some information that allows us to solve for k, and then we're going to use that equation to answer the problem. All right, another kind of good exercise with this section is to kind of get used to the application problems and what information we care about and don't care about, right? So when at a quick glance, I'm like, this is a pretty long paragraph for a math problem, and it feels somewhat intimidating. But once we start to read through this, we're going to see that we really only care about a small section of this paragraph. All right, so when you use a spray can and press the valve at the top, you decrease the pressure of the gas in the can. This decrease of pressure causes the volume of the gas in the can to increase. Because the gas needs more room than is provided in the can, it expands in spray form through the small hole near the valve. In general, if the temperature is constant, and this is where we start to care, see, that's almost most of the problem before we actually care about any information there. It's more just kind of laying some background information. The pressure P of a gas in a container varies inversely as the volume V of the container. Then we're given that the pressure of a gas sample in a container whose volume is 8 cubic inches is 12 pounds per square inch. Right, so let's go ahead and use that information to build the equation, and then we'll go ahead and revisit, figure out what we're solving for. So the pressure P varies inversely with the volume, so that's the pressure P is equal to the constant divided by the volume. Then we're given the fact that the pressure of a gas sample in a container whose volume is 8 inches is 12 pounds per square inch. So the pressure here is actually 12. Right, the volume is 8 cubic inches. Thinking about the units there can kind of help me determine which one is the volume there, since it doesn't explicitly, I guess it explicitly says the volume, but it doesn't explicitly say the pressure. But pounds per square inch is a way that we can measure pressure. All right, so then we can solve for K by multiplying by 8. So we get that K is, that'd be 80, 96. So the equation is that the pressure is 96 divided by the volume. And so then we need to figure out if the sample expands to a volume of 22 cubic inches, what is the new pressure of the gas? So the pressure is equal to 96 divided by 22. Make sure on Math Excel that you're reading how it wants the answer typed in. I would imagine in things like this, it'll probably want some decimal, but it depends on what that decimal looks like. 96 divided by 22, because that ends up being kind of like a repeating decimal. Let's go ahead and just convert it to a fraction. We'll call it 48 elevenths. So it'd be 48 elevenths pounds per square inch. All right, any questions here? Okay. Almost done. The last kind of two things are just combined variation, and then there's also something called joint variation that we'll close out with. So again, it's all about the language. There's not like a specific equation here, but combined variation is going to be described in the actual application itself. So it says the owners of Rollerblades Plus determined that the monthly sales S of their skates vary directly as their advertising budget A and inversely as the price of the skates P. So we're going to go ahead and build an equation for that. So basically when it's direct variation, we're going to multiply that by the constant. When it's inverse, we're going to divide that by the constant. Okay, so their monthly sales S, we still have that constant, varies directly as their advertising budget. So as they advertise more, in theory, they're getting more sales. And inversely as the price of the skates P. Right, so as the price of the skates go up, their sales might go down. Obviously, there's kind of like a exact price that they're wanting to pay if we think about this in terms of the business itself, but that is our equation. Okay, so directly, the direct variation variable goes in the numerator, inverse in the denominator. It says when $60,000 is spent on advertising, so that's going to be A, and the price of the skates is $40, the monthly sales are 12,000 pairs of rollerblades. Right, so we're going to go ahead and find the constant of variation. So we have 12,000 equals the constant that we don't know yet, times the advertising budget, which is 60,000. And then the price of skates is $40. And so we can solve for this. There's a number of different ways you can solve for it. We could go ahead and do 60,000 divided by 40. We could also multiply by 40. I don't know that one's going to be better than the other. I'm going to go ahead and just multiply by 40. I think kind of our habit with solving equations is to get rid of the fraction. So 12,000 times 40 is 480,000. And then K times 60,000. So then after we divide by 60,000, 60, 1, 2, 3, we get that it's just simply 8. So part A says to write our equation of variation, so to be that the sales is equal to 8 times the advertising budget A divided by the price of skates P. And then determine the monthly sales if the amount of the advertising budget is increased to 70,000. We would then assume that the price of the skates is going to stay the same. Okay, so in part B here, we're going to solve for the monthly sales S by doing 8 times the advertising budget of 70,000 divided by the price of skates, which is still at 40. And that's just calculator work. 8 times 70, 1, 2, 3, divided by 40. That's not right. 560, 1, 2, 3, divided by 40. There we go. Is 14,000. So in theory, if Rollerblades Plus increased their advertising budget, meaning they're advertising more and kept the price the same, they are going to increase their sales by $2,000, which kind of makes sense. Obviously, you'd want to weigh in the cost of advertising or how much that advertising goes for. It may not actually be cost effective for them to want to actually up that price there. Okay, all good here? All right, one last thing. And then we kind of have an awkward amount of time left, so we'll see how we spend these last 5 to 10 minutes. All right, last one is joint variation. Got a big paragraph here. I'll just kind of show you a place where we see this. But joint variation is a variation in which a variable varies directly as the product of 2 or more other variables. And so the equation is y equals that constant k times xz. And it reads y varies jointly as x and z. So we'd always be given the 2 variables. Okay, so the rest of this just says that joint variation plays a critical role in Isaac Newton's formula for gravitation. So I would assume that this is the force equals g. G is probably the constant of mass 1, mass 2 divided by distance squared. Or I think it says it here. Let's see how I did. The formula states that the force of gravitation F between two bodies varies jointly as the product of their masses, m1 and m2, and inversely as the square of the distance between them, d. So I kind of had it right. G is the gravitational constant. The formula indicates that the gravitational force exists between any two objects in the universe, increasing as the distance between the bodies decreases. One practical result is that the pull of the moon on the oceans is greater on the side of Earth closer to the moon. Thus, gravitational imbalance is what produces tides. Kind of interesting where that comes from. Anyways, let's just set up one equation for this, and then we'll be done. We probably won't solve it. Just want to work on setting these equations up. And then again, we kind of have the awkward amount of time left here in class. Know that we can also see combined variation here, which we are going to see. So it says the centrifugal force C of a body moving in a circle varies jointly with the radius of the circular path r and the body's mass m, and then inversely with the square of the time t it takes to move about the full circle. Okay, so we're going to go ahead and just set up this equation here. With that centrifugal force, C, we still have our constant, varies jointly with the radius r and mass, so that's r times m, and then with it being inverse of the time t. What you got? Does it say the square of t? Yeah, t squared. Good catch. Good catch. Okay, then just like before, we'd plug in all these values, find the constant, and use that to solve the particular problem. I'm going to spare us that time. I feel like we kind of got the hang of it at this point. So that's it for today. With us having 7 minutes, I'm going to stop this video.